Okay. Let's see. Let us begin. Let's see. What were we talking about last time? We saw we can solve the system by creating an augmented matrix. And performing a reduction. We had 3 situations, only 3. Our system will have exclusively, meaning these don't actually mix with each other, no solution. It's called inconsistent in that case. 2, it will have a unique solution. There will be one set of variables in a particular order that will solve the system, or has infinitely many solutions. There is no in between. And in 2D, it's not that hard to actually see this, because you can actually sketch pictures of what 2 equations might look like. So for example, I can do that line here. Let's say that's, I don't know, y equals 1 minus x. And then I can have another line here, y equals x. And you'll see that they'll meet at one point. That would represent the solution. That's the x and y values that will solve both. I can have another situation where I would have something like y equals 1 minus x, and then I could have something like y equals 2 minus x, and you'd realize this has no solution. There is no x and y where both of those would meet. We're going to use that idea later. Or rather, I'll say I'll have you guys use this idea later, the picture idea, to try to figure something out. Or you can have something like y equals 1 minus x, and y equals, say, 5 minus 5x. Let's write it in a little bit different. 5x plus 5y equals 5. And some of you would of course notice that's actually the same line, because 1 is just reduced by 5. And that's a situation where you have one line right on top of the other. And so like that's the thing. They'll actually look exactly the same. And so here every coordinate is a solution. That gives you infinitely many. Now when it comes to straight lines, there's no other possibility. They'll either intersect once, or not at all, or always. Right? And for straight lines, there's no other possibility. And it turns out, this is true for systems of any size, so it goes up into higher dimensions. So you can talk about in 3D, you can have 3 planes where none of them are touching each other. And that's no solution. You don't have to worry about how sketching planes if you're not going to be in Calc 3. You can have a situation where, like, something like this. This happens twice. This is also no solution. Let me give you one where there's actually a solution. So let's say here you have another one slicing through here like that. Right? So you'll notice that all these planes will intersect on a line. That's an infinite number of solutions. You can have something like what I was trying to draw before. Where they'll literally only intersect at one point. Right? Anyway, this goes up into higher dimensions, 4 dimensions higher than you can imagine. But you can actually use the idea of pivots to actually prove that you either have one intersection, no intersection, or infinitely many intersections. So that's an important thing. And we saw how to recognize this from the pivots. That's going to be important. So in AX equals B, if we augment as A, B, and reduce, then no solution means, and this is all it will ever mean, you have a line, row, like a bunch of zeros and ending with something not zero. Okay, so that we have. We also have. Now, once that doesn't happen, otherwise, if you don't have a line like this, then you are either in one of two situations. Either the number of pivots equals the column number of columns in A. And that means there's a unique solution. Or the number of pivots less than the number of columns in A. That means infinitely many. And I want you to remember how to deal with the situation here. What you would do is set any variable with no pivot in its column equal to itself, and solve for all of the variables in terms of this guy. You could actually have several such guys having that. And that's where we left off with. I think it's good to have that kind of summary in your mind for when you're actually going after problems, trying to solve a problem. You'll either have no solution, one solution, infinitely many. You augment, reduce, you end up in that situation, no solution. Otherwise, you look at the number of pivots. If you have a pivot in every single column, that means every variable you can actually solve it for it, and that would mean a unique solution. If you don't have a pivot in every column, you won't be able to solve for everybody, so some people will be allowed to do whatever they want, and you just set those people equal to themselves. They can do whatever they're currently doing, and then you write everyone else in terms of those guys, and basically you have an infinite number of solutions, because every value that that guy, such a variable takes on, creates a new set of variables that will solve the system. And this is going to work for all of them. Every time you pick a value for one of these guys, it generates a new solution, and you can pick an infinite number of values because they're all real numbers. Okay, so that's where we left off. Very important that you kind of have that in your mind, and very important that you kind of know how the row reduction process works. You need to remember what the echelon forms look like, and then just know there are only 3 legal ways you can move from a situation of not being in one of those forms to being in one of those forms. And once you get there, you should know what it means by actually looking through this. So it's been a whole weekend between now and our last class, so I just want to make sure that everyone is solid on that. That's good. I actually want to talk about one new thing today, which is finding inverses. Then we will go through we'll do something else. So I told you what an inverse was. Right now I'm going to tell you how to find one and why it might be important. I'm going to tell you one way in which it might be important. Finding inverses. Now, normally I prove this using elementary matrices, but this is not that kind of class. Your book kind of tells you, gives you an argument why you might expect it to work out this way, and it kind of shows you a process, but then it backtracks, it kind of brute force. I don't really think it's very insightful, other than, oh, it's kind of cool how that works out. But, so I'm just going to kind of tell you how things work. So recall, a n by n has to be square, is invertible if there exists another matrix which we call A inverse, which is also an n by n, such that if I take A, multiply by the inverse, the result is the identity, and the other way around, you get the identity as well. How do you find this? So now there's a process, there's several processes by which we can find inverses. The most famous ones are ones that, there's one that uses row reduction, which is the one I'm going to show you. There's another one that uses determinants and adjoints, but I'm not going to talk about determinants in this class, so I'm not going to show you that one. So, one way is to use row reduction. And here's going to be the process. Step one. You're going to augment A with In, like so. You're going to put A over here. You're going to put the identity right beside it. The same size identity as A is. Step two, you're going to find the R, R, E, F. You're going to go all the way to the reduced row echelon form. So here represents you finding the reduced row echelon form. And at the end of the day, this is going to end up in a very particular way. It turns out, and your book worked through an example backwards to show you that this will always kind of be the case. Once you put it in the reduced row echelon form, provided this thing has an inverse, the identity is somehow going to appear on this side. And then you're going to have another matrix appearing on that side, and it turns out that's going to be the identity. So, and that's it. Step three. If In appears on the left, A inverse will be the matrix on the right. And if In does not appear, so make sure you're doing it correctly, then A has no inverse. So once it has an inverse, this will work out. Take your matrix, put it beside the identity, do the reduce or echelon form, and for any matrix that has any square matrix that's n by n and has an inverse, that's what the reduce or echelon form of this matrix would look like. And so you just copy off the guy on the right. That's basically it. So row reduction is very useful for multiple things. One way in which it's useful is to find these inverses. Example. Let's do a little general one. Let A be a 2 by 2. A, B, C, D. Now for 2 by 2 matrices, I'm going to expect you to, well, everyone expects anyone who's seen this to remember the formula for the inverse of a 2 by 2. You shouldn't have to go through this process. What I'm going to do is I'm going to go through this process to derive the formula for it. Find its inverse if it has one. And we're going to see when it's going to happen. So, now here's really going to test your imagination. Do you actually understand row operations? Do with letters in it, and that's going to tell you for sure. What we're going to do is we're going to set up A, B, C, D. We're going to put the 2 by 2 identity on the right. Now the point of this is to actually find the reduced echelon form here. So you want a 1 in here, 0 below it. You want a 1 over here, 0 there. And then whatever happens over here with the A, B, C, D, you're going to realize that that gives you the inverse. What would be a first step here?
You
can't set equals 1. That's
or like get it so that.
Yeah. How would you do that? You can divide the entire row by A. Here's what I would say though, and this kind of is a general thing, which I'm going to talk about after doing something longer like this. You probably want to avoid fractions if you can. So let's actually just keep things whole here for a moment. So let's just kind of keep this whole as A and just know at the end I can divide through by whatever I want. So let's focus on creating the zeros first. So I know eventually I'm going to divide through by whatever I have to in order to get a 1 here. Until then, how would I create a 0 here?
Subtract C.
How would subtract C? How? You forget the moves we can do? You can swap rows. You can multiply a row by a non-zero constant. You can add a multiple of a row to another row. Anything else you do is illegal. Using only those 3 moves, how do I get a 0 here? Yeah?
Row 2 minus, some coefficient times row 1.
What's that coefficient going to be?
It depends on what A and C are.
Does it? Can you tell me something that's always going to work?
Like A over C maybe?
A what?
A over C and then you can
Let's avoid fractions. If you didn't want a fraction, what would you do? Not that it's wrong, but it's going to make your life a lot easier. Not having to. Remember, you're going to be doing a lot of calculations here. You don't want to have to do with fractions. Let's say you had a 2 and a 3. Blah, 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 blah. How do you make that a 0?
You can multiply the bottom by 2 and the top by 3 and subtract it.
Okay. Yeah. How do you make this a 0?
So multiply the bottom divided by A over top by C, etc.
This is what it means to think mathematically, right? If you need help, just put numbers in there and kind of figure out what would I do. Sometimes you put letters in places and people just forget how to think. There's this joke where it was like, then the devil said to Eve, put the alphabet in math. You guys saw that? Yeah, that was fun. Yeah, some of you try to do algebra now and then everyone forgets how to like add and subtract and what they would do. No, if you had two different numbers, you multiply each one by the other one to get the products to be the same, and then you can subtract. So what I can do now is I can take, so this is row 1 times C, and this is row 2 times A. In fact, I can make it a little bit nicer so we can add. Let's put out a negative here. Row 1 times minus C. And now I'm going to add those two, row 1 plus row 2. This plus that, 0. This plus that, AD minus BC. This plus that, minus C. This plus that, A. And I can go back to the original here. Now moving to the next line, let's say I want to actually it might be nice to keep this here. So now if you want to eliminate this guy, what would you kind of do? Well, because we know we have those 3 operations, pretty much the only thing here that's going to work is if I multiply this by something, that's going to actually create the same thing down here. So what are you thinking here? What can we do to get that one? Maybe that's 345, right? I want to make sure I have enough time for something else.
Wait, are we trying to get the one in the top?
I want to get 0 here. It's going to be hard getting that sum, right? So maybe what you can kind of start to do here is maybe, let's, because we don't know what these numbers are specifically, maybe I'll start to do a little fractions here. So what I can do is something like the following. I am going to divide through by AD minus BC. So I get the second row behaving how I want. And by the way, by me dividing by this is going to kind of hint you when this guy would actually exist. So that's going to be a 1 here. And what I can do then is do something like well, we don't have to divide that. I don't want to force us to divide by 3 actually. So what I can do now is do something like, I'll do it in 2 steps so you can kind of see where I'm going with this. Multiply this by D. And what I want to do now is say, take this and subtract that. So I'm going to take row 1 and subtract row 2 times b. So a minus 0, that's just a. B minus b, that's 0. 1 minus this, well, that's just AD minus BC over AB minus BC minus what's going to be plus BC over AD minus BC. And 0 minus that is going to be minus A over AD minus BC. So we're going to do this. Now moving over here, this guy is just going to simplify to AD over AD minus BC. This guy is just going to be minus AB over AD minus BC. This guy is going to be, let's see, AD minus BC. And this is going to be AB over AD minus BC. 0, B. And now I can actually just get this to be a 1 by dividing this through by A. Row 1 divided by A. And then this I can get to be a 1 by dividing through by D. Row 2 divided by B. And now, what I want you to recognize is that there's the identity here, which means that this guy here is actually our inverse. Now, I'm going to factor out a common term here. Notice that everyone is divided by AD minus BC. That's just a number. I'm going to move it outside. 1 over AD minus BC. So what's going to left over inside when I take them off is just the numerators. It's going to be D minus B minus C and A. And that's actually the formula. And now I want you to note AD minus BC cannot be 0. That's actually an important note. I'll put that in the box as well. And so that gives us a theorem. By the way, this expression AD minus BC, it is what's called the determinant of the 2 by 2 matrix, but don't worry about that. For you guys, it's just some number. So this leads to the theorem. If A equals A, B, C, D, and AD minus BC is not 0, then A is invertible and A inverse equals 1 over AD minus BC times, and so AD minus BC, we usually look at this as a cross multiplication. We don't look at it like that. This times this minus that times that, check if it's 0. If it's not 0, it has an inverse, and then what you're going to do to compute the inverse, you switch the guys on the main diagonal, so the D goes up here, the A goes down there, and we change the sign of these two. And that's always going to be how it actually works. So this is actually something that you should memorize. So if you ever have to find the inverse of a 2 by 2, that's going to be it. Now for anything larger than a 2 by 2, the formula is going to be very ugly. People usually don't memorize the formulas for those. They rather just stick to one of the processes. So for us, we're just going to stick to the row reduction process. Let's actually do an example of this. Suppose A equals 1, 2, 3, 4. Is A invertible? If so, find its inverse. Okay. Is A invertible?
Yeah.
Yeah, look at this times this, 1 times 4, minus that times that, 2 times 3. You'll get 4 minus 6, this gives you minus 2. This is not 0, so yes, A is invertible. B, what is its inverse? Well, I'm simply going to follow this formula. It is 1 over AD minus BC. That's 1 times 4 minus 2 times 3 times, I'm going to swap these two. 4, 1, change the sign of the other two. Minus 2, minus 3. So this becomes, so that's 4 minus 6, which is minus 2. This is minus 1/2 times 4 minus 2 minus 3, 1. And that's actually your answer. Now, 1, we can check this to verify. If that is in fact the inverse, and this crazy thing that I just derived here is actually working, what we will notice is that if I take A times the inverse, that should give me the 2 by 2 identity. And let's actually see. This is 1, 2, 3, 4, and I'm going to multiply that by minus 1/2, 4 minus 2, minus 3, 1. Now, one thing that the homework taught us is that with numbers, we can actually change the order. I can take this minus 1/2, put it in front. Okay. Then we can multiply the 2 by 2's. 1 times 4 plus 2 times minus 3. 1 times minus 2 plus 2 times 1. Then going to the second row, 3 times 4 minus 4 times 3. And then the last one, 3 times minus 2 plus 4 times 1. I'm going to simplify that. So that's what? Well, minus 2, right? This is 0. This is 0. This is minus 6 plus 4, that's minus 2. If I multiply this in, get the identity. So that actually works. This is actually the answer. Somehow that crazy experiment worked out. Questions on this? Well, I shouldn't say that. Just know the formula for the 2 by 2. This is one of the cases where I'm not going to say, you don't need to know how to derive it. No, you do need to know the process for finding this, because you're going to need to use this process for anything that's a 3 by 3 or bigger. You're going to have to do row reduction to actually compute the inverse. We're going to do an example. So yeah, but for 2 by 2s, you should just know the formula. Or you can do row reduction. You'd actually end up with the same thing. Put this guy beside 1, 0, 0, 1. and find the reduced or echelon form, and you'll actually get this on the right side. Where do I want to go? Okay. Over here. I'm going to give you one way in which this is useful. There are many ways in which an inverse is useful. One way in which the useful way in finite math. One way in which finding inverses are useful. Suppose we have ax equals b. So this is just, remember, a generic term for a system of linear equations. And a is invertible. Then A inverse exists, and it's something that exists. We can start to multiply both sides by it. We can actually do that. I can take A inverse and multiply both sides of my system. Now what happens here? What is that equal to? A inverse times A. By identity. And what's that equal to? The identity times this thing. Just the guy. That's the point of the identity. You multiply it by anything, it just gives you the thing back. Okay. And so what you realize is that you can actually solve the system using an inverse matrix by multiplying it on the right. Now, by the way, this also, so we can solve the system AX equals B via X equals A inverse times B whenever A is invertible. Now I want you to know, I mean, if you think about it, it'll make a lot of sense, but this is just one matrix times another. They both have just numbers in them. So you'll get a matrix as the answer where there's no ambiguity, there's no real variables in it. So this implies there is a unique solution in this case. There's only one set of answers. So that kind of tells you something else. If you're looking at a system where the coefficient matrix does not have an inverse, then you know you're in one of two cases. You either have infinitely many solutions or no solutions. You never have a unique solution case. Conversely, if you're looking at a system where the coefficient matrix is invertible, it's a square system and it's a square matrix and it has an inverse, then you're guaranteed to have a unique solution, and that's going to be the formula that gives you that solution. Let's actually do an example here. Say that's the system. There are many ways you can solve the system, but I want to specifically use the inverses idea. Note, A equals 1, 2, 3, 4 is the coefficient matrix. And we saw A inverse is actually minus a half times 4, 1, minus 2, minus 3. I wonder what would happen if I take this and multiply that. Let's see. So first of all, there's a certain order that that has to go into because this is a 2 by 2 and our B is a 2 by 1, which means I have to multiply it so that the A inverse is on the left, which is what the theorem says anyway. So note that if I take A inverse times B, this is going to be minus 1/2, 4 minus 2 minus 3, 1, 2 minus 1. Do our matrix multiplication. This is 4 times 2 plus minus 2 times minus 1. And that's it. Then what I'm going to do is minus 3 times 2. Plus minus 3 times minus 1. So this is minus 1/2 of, this is 8 plus 2, it's going to be 10. And this is going to be minus 6 plus 3, minus 3. So this is going to be minus 5 and 3 over 2. My arithmetic was okay?
Why
Yes.
are we multiplying by negative 3? Like negative 3 by 2 and then negative 3 by negative 1 and not 1 by negative.
Oh, because I'm doing matrix multiplication. So I'm taking this row times that column. So it's the minus 3 times the 2 plus the,
Yeah.
oh, you are. This should be, this here is a 1. Right?
Positive.
That would be
Negative 7.
negative 7. Yeah. Great. So that would be rather embarrassing. But I'm going to be like, look at this, and then it doesn't work out. Okay, so where are we? 7 over 2. Okay, so now here's what I'm saying. Let x equals minus 5 and let y equals 7 over 2. Seems like weird numbers, right? But what if I take x plus 2 times y? So if I take x plus 2 times y, this is going to be minus 5 plus 2 times 7 over 2. That's going to be minus 5 plus 7. That is 2. Oh, okay. And then if I take 3x plus 4 times y, that's going to be 3 times minus 5 plus 4 times 7 over 2. That is going to be minus 15. That's going to end up being plus 14. That's going to give me negative 1. So turns out that those guys actually check out. This is in fact the solution to the system. Yeah. So you can find an inverse of a 2 by 2 by that formula I gave you. And one way in which an inverse is nice is if your coefficient matrix of a system is an invertible matrix, you can actually find the solution by taking the inverse times the answer called the constant matrix over here. Let's do one together. Somehow I actually lost my notes for today. That's why we started late. I was like, where did I put this thing? I don't know what happened. So we're kind of winging it. But it's easy to not have nice numbers here, so I was looking for something with a nice number. So let's do some practice. Let A equals, let's do a 3 by 3. Find A inverse. And with the end of this example, I won't say we're not going to use matrices anymore because we are, but this was just the last kind of thing I wanted to teach you about matrices. So for the rest of the course where we're using matrices, you now know everything you would need when you actually come up on that situation. Inverse was the last thing I had to tell you guys about. So, I'll show you how that's going to work. You are going to take the matrix 1, 3, 1, 2, 2, 1, 2, 3, 1. You're going to put it beside the 3 by 3 identity matrix. And now you're going to find the reducer echelon form, which I know. Did a lot of examples last week. You guys are getting it, but I don't know, it's been a long weekend. Let's make sure we actually, yeah, so again, remember we want to focus our game plan on the pivots. So I want the top leftmost one, that's going to be the 1. So that's already a 1, so I'm not going to bother it. So I'm just going to copy back a row 1. But I immediately want to have zeros below it. Remember that should be your goal if you want to be efficient. So now you're kind of thinking, well, how can I get a 0 here? There are a couple ways. I can do row 3 minus row 2. Right? This minus this, 0. This minus that, 1. This minus that, 0. This minus that, 0. This minus that, minus 1. This minus that, 1. So I can do the third row minus the second row. Now I have to use 2 other rows to get this 0 here. And what I can do is something like take 2 times row 1 and then minus row 2. Or maybe even minus row 3. It's minus row 3. So 2 times this, minus that, 0. 2 times this is 6, minus that, 3. 2 times this is 2, minus that, 1. 2 times this is 2, minus that, 2. 2 times this is 0, minus that, 0. 2 times this is 0, minus that, minus 1. And we have that situation. So this pivot is established. He's sitting pretty nicely. He's the only 0 in this column. I want to establish this one now, so I want to get a 0 below that. Now how am I going to get a 0 below that? Well, what I want to do here I can take 3 times row 2 and say row 3 minus 3 times row 2. 0 minus 3 times 0, 0. 3 minus 3 times 1, 0. 1 minus 3 times 0, 1. 2 minus 3 times 0, 2. 0 minus 3 times negative 1, 3. And minus 1 minus 3 times that, minus 4. So here I have all my pivots lined up, cascading off to the right like we wanted. Zeros below them, so now I want to start working on zeros above. I'm going to focus on this guy to kill that guy. In Go over last week, I was like using colored stuff to mark everything. But I'm assuming here we're comfortable enough to actually follow along, at least follow these steps here. So I'm going to change row 1 by just subtracting row 3 actually. And row 1 minus row 3. So 1 minus 0, 1, 3 minus 0, 3, 1 minus 1, 0, 1 minus 2, minus 1, 0 minus 3, minus 3. So 1 minus row 3. 0 minus a minus 4, positive 4. And we have one more thing. This guy. Want to kill that and make that a 0, then we get the identity. What I can do is something like, huh? Row 1 minus 3 times row 2. Yep. So this minus 3 times that, 1. This minus 3 times that, 0. This minus 3 times that, 0. This minus 3 times that, minus 1. This minus, what? This one was this minus 3 times that gives me a plus 3, and so that'll be a 0. This minus 3 times that, that'll leave me with a 1. And I think everyone else is cool. So this means that the inverse for this matrix is minus 1, 0, 1, 0, minus 1, 1, 2, 3, minus 4. Did we make a mistake? Let's actually check it to find out. It's a long way. So what I can do is I can take this guy, 1, 3, 1, 2, 2, 1, and 2, 3, 1. I'm going to multiply it by that, what I just got. And if everything went okay, this should give me the 3 by 3 identity. So let's see. I have 1 times minus 1 plus 3 times 0 plus 1 times 2. Then I have 1 times 0 plus 3 times minus 1 plus 1 times 3. Then I have 1 times 1 plus 3 times 1 plus 1 times minus 4. And I'm going to have 2 times minus 1 plus 2 times 0 plus 1 times 2. Then I'm going to have 2 times 0 plus 2 times minus 1 plus 1 times 3. Then I'm going to have 2 times 1 plus 2 times 1 plus 1 times minus 4. Then I'm going to have 2 times minus 1 plus 3 times 0 plus 1 times 2. 2 times 0 plus 3 times minus 1 plus 1 times 3. Then 2 times 1 plus 3 times 1 plus 1 times minus 4. And let's just simplify that over here. Okay, moment of truth. Minus 1 plus 2, that's a 1. 0 minus 3 plus 3, that's a 0. 1 plus 3 minus 4, that's a 0. Minus 2 plus 0 plus 2, that's a 0. 0 minus 2 plus 3, that's a 1. 2 plus 2 plus minus 4, that's a 0. Minus 2 plus 0 plus 2, that's a 0. 0 minus 3 plus 3, it's a 0. 2 plus 3 is 5 minus 4, it's a 1. We did it. Okay. I think we have enough time for the next thing. So Because I'm sure you guys are aware, I emailed the class a few days ago saying that I was changing the syllabus and we'll start having quizzes from now on. So, and I said today would be the first quiz. So you guys put your stuff away and we'll get started.
You know you got me on that one.
Pass the fry and
We need
Yes.
a couple more.
What?
I think I knew
Oh, I didn't. I just, my heart just
How many? Oh, the whole row.
Well, no, my did it. Apparently, my professor I haven't gotten any other emails, and she doesn't know what she's like.
Yeah, so use the next, the remainder of class to start working on these. Finish working on them at home. We'll actually start next class by going through them. And then we'll start to do an entirely new topic next time, which I think is going to be fun. It's a little bit more fun than linear systems. We're going to talk about linear inequalities. It's going to be really awesome. I'm not collecting it, but we'll go through it next time, but it's to your benefit to actually try it before you see me go through it. So I'd at least like to see you guys get through the first problem because that was straight up what I just taught to kind of reinforce things.